to a video about motion, force, work, simple machines, everything we just did in the last unit. Okay, so this first standard is going to have 3 questions about it, and you are looking at analyzing motion using math and graphs. And so we're not going to spend a lot of time going through the math today. That's in another PowerPoint, but we are going to look at the graphs. So whenever you see a motion graph, the first thing that you want to do is you want to check out the y-axis. Why? Because if you don't, you'll get it wrong. Okay? So this one is a distance versus time graph. And so on the y-axis is distance, on the x-axis, of course, is time. So when you're reading this, the line is showing you how much the distance is changing over time. So when you have a nice straight linear line right here, if it's a really steep line, like the screen one, then that means that you're speeding really fast because you're covering a big difference in distance in a short amount of time. Okay? If you look at the red line, they're still going a nice steady, constant speed. You have a nice straight line, but they're not going quite as fast because if you compare the two distances, they went a lot less in the same amount of time. If your slope is 0, like in this region right here, that means that your distance isn't changing. Well, if your distance is not changing, then that means that you're standing still. If you have a negative slope, so your distance is in the negative direction, then that just means you're going back to where you started. Okay? And then if you have a curved line, then that means your rate of change is not constant, which we know means that you are accelerating. In this case, you are going faster, so you have a positive acceleration. If they give you a graph like this and they ask you to calculate speed, then they're asking you to find the slope. So you're going to do rise, which is distance, over run, which is time, which is exactly the same as the formula for speed. Alright? Which is, of course, distance over time. Okay? Remember that speed is the distance that's covered in a certain amount of time. An example of that would be 35 meters per second, whereas velocity is speed in a certain direction. Okay, that is called a vector quantity, which means that has 2 parts. It has not only your speed, but also the direction that you're going in. So an example of that would be 35 meters per second east. So be very careful with that and knowing the difference between those two. And then, of course, I have your triangles if you're calculating speed or velocity. All right, the next graph that we're going to look at is a speed or velocity time graph. So again, the first thing you want to do is you want to check out your y-axis. In this case, you have velocity on the y. So you read this totally different than the other graph. So this time, if you have a slope of 0, that does not mean you're standing still. That means that your velocity is not changing, which means you're going a constant speed in a constant direction if this is velocity, or in one direction, one speed, you're not accelerating. If you have a nice straight line, this means that you have a really fast acceleration. If you have a negative slope, you have a deceleration or a negative acceleration. So the jet would be accelerating faster than the race car. That's pretty logical. And then if you have a curve, it's not linear, then that means you are accelerating, but you're not accelerating at a constant rate. Okay? And then you could also have a line that looks kind of like that, and that would mean that you're slowing down, but again, not at a constant rate. If you had a graph like this and you wanted to show standing still, and you would have a straight line at 0, meaning that you are going 0 miles an hour. So be really careful and make sure that you're checking out the y-axis. That's super important. If they give you a graph like this and they ask you to calculate acceleration, they're asking you for slope. So you would do the final velocity minus the initial velocity divided by the time that you traveled for. Okay? So acceleration is a change in velocity. And remember, velocity has not only a speed, but also a direction, which means there are 3 ways that you can accelerate. You can speed up, you can slow down, or you can turn. A lot of students forget that spinning in a circle, even at a constant speed, is considered accelerating, or turning at a constant speed is also considered accelerating because you're changing your direction, so be very careful with that. Asking you to calculate acceleration just means plugging numbers into the formula. Final velocity always goes first, minus initial divided by the time that's taken. If you are slowing down, your final velocity should be less than your initial, so your answer needs to be negative. You cannot have a negative time. Be very careful about that. So, if you are speeding up, your answer should be positive. So be very, very, very careful and make sure that the number makes sense and you're not just plugging things in. Alright, the next thing is going to be Newton's laws. I'm talking about the relationship between force, mass, velocity, and acceleration. There are 4 questions about this. So the first thing we want to review is forces. And we looked at some force diagrams a while ago, remembering that a force is a push or a pull. We measure force in newtons. If the arrows are going the same way, if the arrows are going opposite ways, you're going to subtract them. So in this first example, you have a force of 1200 newtons up, and then the force of gravity, 800 newtons downward. Because these arrows are in opposite directions, you're going to subtract them. Your net force would be 400 newtons up. Why up? Because that was the bigger force. Okay? Let's look over at this third example. Your object is going to have a net force of 20 newtons to the left. Up and down are equal, which means they're balanced. 50 minus 50 is 0. So the object is not going to move up or down. It is only going to accelerate or change its motion 20 newtons to the left, because this is an unbalanced force. Remember that mass is the amount of matter that is in an object, okay? And that we traditionally measure in kilograms. You might also see it in grams. And then that brings us, I keep having to move my face around, sorry. That brings us to Newton's first law, which says an object at rest will remain at rest, an object in motion will remain in motion unless acted on by an unbalanced force. We also call Newton's first law the law of inertia, which is an object's tendency to doing whatever it's doing, okay? It doesn't want to change. In order to change an object's motion, you have to have an unbalanced force, okay? Lots of unbalanced forces that you don't think about that naturally take place, like gravity and friction, okay? And remember, the more mass something has, the greater force it's going to take to change its motion, okay? We'll talk about that in Newton's second law. So Newton's second law has an equation that goes with it, which you guys have done in math class, and it says that force is equal to mass times acceleration. Okay, and so basically, if you want to change something's motion, you want it to accelerate, speed up, slow down, or turn, then you have to put a force on it. And if something has a big mass, it's going to take a greater force to cause it to change. And that's because more mass means more inertia. So if you have a soccer ball and a bowling ball, the soccer ball obviously has less mass. So in order to get it to move, it's going to take less force. Okay? Alright, Newton's third law. Every action, there's an equal and opposite reaction. So be very careful about this. Students forget that objects put force back on you. So if you punch the wall with 100 newtons of force, the wall is going to push back on you with 100 newtons of force. Okay? If you push down on the table with 25 newtons of force, the table is going to push back on you with 25 newtons of force. So equal and opposite, those are the key words there. And you can see that in these 4 pictures on the screen. Alright, your next topic is going to be looking at data to talk about the relationship between mass and gravity for objects that are falling. Okay, so the first thing we want to talk about is we want to talk a little bit about gravity. And gravity is an attractive force that pulls objects to the center. For us, we say down, which is the center of the Earth. Okay, there are 2 ways that you can affect the strength of gravity. It's stronger when objects have a greater mass, or if they're closer together. So if you want to increase the gravity, you would need a greater mass, or to push things closer, which you can see in this picture here. Everything that has mass has gravity. You have the force, but you just don't notice it because you're standing on Earth, which has such a big gravitational force, it kind of overshadows force. Alright, talking about the difference between mass and weight, Remember that weight is going to increase if your gravity increases, but mass is not going to be affected by a gravitational force. We said earlier that mass is the amount of matter in an object, whereas weight is how gravity pulls on your mass. Okay? So if you look at these pictures, your mass stays constant even when the gravity changes. On the sun, your weight would be a lot because the force of gravity is so great, because the mass of the sun is so great. Okay? Whenever you see newtons, you always know that that's weight, because weight has to do with gravity, which is a force, whereas mass does not. All right, let's talk about free fall. If there was no air resistance and you were in a vacuum, like in outer space, then the only force acting on an object would be the acceleration of gravity, which is constant and it doesn't depend on your mass. So that means that all objects would fall at the same rate. Doesn't mean they hit the ground with the same amount of force, but it does mean that they would fall together. So free fall is just the vocabulary word that means a situation where there's only gravity present and we're not looking at air at all. So if an object is in free fall, it's going to accelerate at a constant rate, which on Earth is about 9.8 meters per second squared, which means every second that you fall, you go 9.8 meters a second faster. So the longer that you fall, the faster you're going. Until, if we talk about terminal velocity is when the two forces that you see in falling objects on Earth are balanced. Gravity, which is pulling down, and air resistance, which is opposite, pushing back up. If those forces are balanced, thinking back to Newton's first law, then an object will stop accelerating. That does not mean you stop falling. It just means that you stop speeding up. Okay, you've hit a maximum speed. Remember, terminal means end. So you've hit that max velocity. You're not going to go any faster. So if you look at this picture here, in the first example, their acceleration is 9.8 meters per second. As the air resistance increases, you start to accelerate a little slower until finally your acceleration is zero. Again, that does not mean that you are not moving. It just means that you're no longer speeding up. You're falling at a constant speed in a constant direction. All right, and our last standard. There are 3 questions about this where we're talking about work, mechanical advantage, and simple machines. All right, so in order in science to be considered work, a force has to move an object a distance, and they have to be in the same direction. So if an object doesn't move in the direction of the force, then it's not considered work. So make sure you check out this visual over here, okay? Carrying the groceries is not considered work because her force is upward, but her direction is forward. The arrows have to go the same way, like when she's lifting the groceries. No matter how hard you push on the wall, if the wall doesn't move, it is not work. Okay, there is an equation for work. Work is force times distance, which you can see worked out on the right-hand side. Remember that there's a force-distance trade-off. You cannot change your work. So that means all we can change is our force or our distance. So what we do with simple machines is we try to apply a smaller force by moving something a greater distance. So in a lever, that looks like us moving the fulcrum closer to the load to increase the distance of our effort. All right. Mechanical advantage tells us how good a machine is. And very quickly, if you are talking about a ramp or a ledge, in order to increase the mechanical advantage, you want to increase the length of the ramp or the wedge. The length would be here. Your height's going to stay the same. If you're talking about a screw, you would need more threads, which means you're going to turn it more times. Again, you're increasing the distance and decreasing the force. With a lever, you're going to move the fulcrum closer to the load. With a pulley, you need to add more pieces of rope or lengths of rope. And then with a wheel and axle, you would need a bigger radius of the wheel. Think about a school bus. You're turning it a further distance. And that brings us to the end. Happy studying. You're going to do great. See you later.